In this video, we will be looking at section 3.5, which covers real zeros of polynomials. The first thing we're going to look at is if we can narrow down where all of the zeros might be. So we're going to talk about Cauchy's bound. It says, given a polynomial f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down to a sub 1x plus a sub 0, let m be the largest of the coefficients in absolute value. Then all the real zeros of f of x lie in the interval. Notice that these are closed brackets, so the endpoints may be zeros. We have negative m over the absolute value of a sub n minus 1 to positive m over the absolute value of a sub n plus 1. I wrote this down on a sticky note so we can use it in the future. Notice that a sub n is our leading coefficient, and like it said, m is the largest coefficient in absolute value. So let's see what we can do with this. It says let f of x equal x cubed plus 4x squared minus 11x plus 6. Determine an interval which contains all the real zeros of f. So we know that all of the real zeros will lie in this interval. So we need to figure out what a sub n is and what m is. A sub n is our leading coefficient. So I find the highest power on x, that would be an x cubed, and the coefficient on that term is 1. So my a sub n is going to be 1. Now m is the largest coefficient if we take the absolute value. So what that's saying is ignore all the signs. Which coefficient is largest? So we have 1, 4, 11, 6. 11 is the largest, so our m value will be 11. So if we now plug into this interval, we will have square bracket, negative, we put our m value in the numerator, over the absolute value of a sub n. Looks kind of weird having the absolute value of 1. Sorry about that. Minus 1, comma, m over the absolute value of a sub n plus 1. Let's simplify that. That's going to be negative 11 over the absolute value of 1 is 1, minus 1, comma, 11 over 1 plus 1. Negative 11 over 1 is negative 11. Negative 11 minus 1 is negative 12, and 11 plus 1 is 12. So if we want to find all of the real zeros of this function, they are going to lie between negative 12 and 12. What this does is it helps us narrow our search. We don't have to look all the way from negative 2,000 to positive 2,000 to find the real zeros. They are all going to lie between negative 12 and positive 12. Now we're going to look at the rational roots theorem. It says, given a polynomial f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down to a sub 1x plus a sub 0. So we have a polynomial with integer coefficients. If r is a rational zero of f, then r is of the form r equals plus or minus q, where p is a factor of the constant term a sub 0, and q is a factor of the leading term a sub n. This is going to sound kind of confusing, but once we do an example, it should make a little bit more sense. So we're going to use all of our rational roots are going to be in the form of plus or minus p over q. P are the factors of the constant term, q are the factors of the leading coefficient. So we're going to try this. It says use the rational roots theorem to make a list of possible rational zeros. Then use division to find the zeros of the polynomial. So we're going to start by finding our p and q values. So p are all of the factors of our constant term. So the factors of 6. What is 6 divisible by? 1, 2, 3, and 6. Q are the factors of our leading coefficient. Oops. So we have x cubed, leading coefficient is 1, So our q values can only be 1. So that means our rational zeros are r, and they are in the form plus or minus, and then we put all of our p values over q. So we could have plus or minus 1 over 1, so we take p as 1 and q as 1. We could have plus or minus 2 over 1, so if p is 2 and q is 1. We could have plus or minus 3 over 1, and plus or minus 6 over 1. So that means all of our rational roots are either plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So those are all of the possible rational zeros. It wants us to use division to find which ones actually are the zeros. Now, we have graphing calculators, so we're going to put them to use. So I'm going to go to my y equals and type in x cubed plus 4x squared minus 11x plus 6. Now I know all of my rational roots are between -6 and +6. So I want to make sure all of those are going to be in my window. So my x minimum goes to -10, my x maximum goes to 10. So I'm going to see everything between -10 and +10, which is all of these if they exist. So let's see what the graph looks like. So now I'm going to use my calculate. So I'm going to go second trace, and I want to calculate the 0, which is number 2. This one appears to be between maybe -8 and -4, so we'll type -8, -4. It kind of looks like -6, so I'll pick a guess of -6. Yep, it says x equals -6 is one of my zeros. Now let's check this other one. Second calc, the 0. It looks like it's at 1, so we'll say it's between 0 and 2. I'll guess that it's 1, and it says there's a 0 at x equals 1. So now we're going to check them. That way we can make sure we have the right answers. I'm going to use synthetic division because it's quicker. So for synthetic division, we start by listing out our 0, which is -6, and I put it in a box. And then I list out the coefficients of my polynomial. We have 1x cubed, 4x squared, -11x, and a +6. I leave a space and put a line. I bring down the first number, 1, and then I multiply. 1 times -6 is -6. I add, 4 plus -6 is -2. I multiply. -2 times -6 is +12. Then I add, -11 plus 12 is 1. 1 times -6 is -6. I have a remainder of 0. Remainder of 0 means yes, this is in fact a 0. Now I'm going to check x equals 1. So I'm just going to continue on with the polynomial I already have and keep doing synthetic division. And I'm going to check +1. So since I already have it, I'm just going to keep working. I'm going to do my synthetic division just like I did previously. I bring down the 1, multiply, add, multiply, add. I got a remainder of 0. So 1 is still a 0. But if you remember looking at the graph, at x equals 1, the graph kind of looked like a parabola. So hypothetically, this should have a multiplicity of 2. So I should be able to synthetically divide in 1 again. So I'm going to try that. If we do that, I bring down my 1, multiply, add, I get a remainder of 0. So that means my zeros, I got remainders of zeros in all of these cases, my zeros are at -6, +1, and +1. We could list it as -6 and +1. We just have to know that +1 has a multiplicity of 2. Now we're going to try this again, but with one that has a few more factors. So we're going to look at f of x equals -2x cubed plus 19x squared minus 49x plus 20. So let's start with our p and q values. P covers all of the factors of our constant term. The factors of 20 are 1, 2, 4, 5, 10, and 20. Our Q values are the factors of our leading term, our leading coefficient. We're going to worry about signs later, so the factors of -2, or we're thinking +2, are just 1 and 2. Here's where things get a little funky, because when I start figuring out my R values, I'm going to need some space here. We could have plus or minus. What I'm going to do is I'm going to take each P value and put it over each Q value. So I'll have 1 over 1 and 1 over 2. Then I'm going to do 2 over 1 and 2 over 2. Then I'll do 4 over 1 and 4 over 2. Five over 1, 5 over 2. 10 over 1, 10 over 2. Then 20 over 1 and 20 over 2. Ran out of room. Let's simplify these guys. A little bit more. So our R values could be plus or minus 1, plus or minus 1/2, plus or minus 2. 2 over 2 is 1, and that's already on our list, so we don't have to write that again. We have plus or minus 4. 4 over 2 is 2, so we don't have to write that one again. 5 over 1 is 5. 5 over 2, we don't have that one yet. 10. 10 over 2 is 5. 20. And 20 over 2 is 10. So these are all of our possible rational roots. That's a lot to choose from. So let's go to our graphing calculator and see if this can help us out. In our y equals, we want to put our -2x cubed plus 19x squared minus 49x plus 20. For my window, my zeros could be as far away as -20. So I'm going to let my x minimum be -25 and my x maximum be 25. That way I can see all of them if they're in there. And just so I don't have 50 tick marks in there, I'm going to say put tick marks every 5. I don't really need to change my y's because I just need to see where these go through. So let's take a look at my graph. Oh man, it doesn't look like anything happens really on this left side or far on the right side. I'm going to zoom in a little. So for my window, let's make my x minimum maybe a -5. And maybe my x max can be 10. And I'll put tick marks every one, see if we can see what's going on there. Well, that's a little bit better. Yeah, I can really see what's going on there. So it's just kind of testing and seeing what works. So I'm going to calculate these zeros to see what we got. Calculate the zero. The first one looks to be between 0 and 1. And it looks like it's telling me 1/2. Let's calculate the 0. It looks like it's at 1, 2, 3, 4. So we'll say it's between 3 and 5. I'm guessing it's at 4. Yep, there's one at 4. And it looks like there's one at 5. So we'll calculate the 0 between 4 and 6. I'm guessing 5. So it looks like 5 is another 0. But we're going to still synthetically divide, make sure that these are the zeros. Maybe I typed something in wrong, who knows. So we start with one of our zeros. It doesn't matter which one. I really don't want to do the fraction, but we'll try it. If we start with our fraction 1/2, I list out my coefficients. So we have -2, 19, -49, and +20. Draw my line. Bring down the -2. -2 times 1/2 is -1. When I add, I get 18. 18 times 1/2 is 9. If I add, I get -40. Negative 40 times a half is negative 20. I add, I get 0. That wasn't as bad as I thought it'd be. Having a fraction you'd think would make it really scary, but everything worked out okay. Because I got a remainder of 0, I know that 1/2 is one of my zeros. Next up, let's try 4. I bring down the negative 2. I multiply, I get negative 8. I add, which gives me 10. I multiply, which gives me 40. I have a remainder of 0. So 4 is one of my zeros. Let's check 5. I bring down the negative 2, multiply, negative 10, add, I get 0 as a remainder. Yes, this one checks out too. So my 3 zeros are the 1/2, 4, and 5. What's kind of neat, and I know we've talked about it a little bit but not a lot, is the number of zeros is going to match the highest power on x. So in both of these cases, we came up with 3 zeros because the highest power on x is 3. Now in the last one, we had 3 zeros, the negative 6, positive 1, and positive 1. So that's where this multiplicity comes into place. So even though there's only 2 zeros, negative 6 and positive 1, because that positive 1 has a multiplicity of 2, that gives us our 3 zeros. We're going to notice moving forward that sometimes our roots are not rational, and sometimes they're not even real. But this will start leading us there.